All right. Hello, everyone, and welcome to the October System Spacing Track call. My name is John Bloss, and we'll be hosting this call along with Jim Louse. To kick us off, I'll go over a few announcements before we get to the topic at hand today. CART System Spacing Track is looking for additional volunteers for the steering committee. So if you have any interest in helping shape the content that is presented each month for the System Spacing Track calls, please contact either Brian Haymore or Matt Smith to learn more. Also, just a reminder, SIG HPC Pros will have a workshop at SC. It will be on Sunday, November 12th from 9 a.m. till 12:30. So if you have not already signed up for that workshop, please consider doing so. Additionally, we will be having a joint social with the SIG HPC Pros group, which will be held at Lucky Strike Bowling that evening from 6 to 8 p.m. This event will be sponsored by ANSYS and AWS, and more details will be forthcoming in the next week. So with that, let me introduce our speakers for today's topic. First, we have Matthew Scambati from Idaho National Laboratory and Xin Leong from Washington University in St. Louis. For the topic today, we will be discussing the evolving landscape of high-performance computing and the quest for portable, reproducible, and maintainable software. As HPC systems continue to grow in complexity and diversity, traditional methods often grapple with the unique demands posed by these environments. Enter the realm of containerized HPC, a confluence of traditional HPC systems and modern container technology. During this meeting, we'll hear two presentations that stem from the insights shared at PERC 23. The first presentation offers a pioneering strategy for building containers tailored for HPC applications, emphasizing software quality assurance through layering. With the second presentation, we'll see a tangible glimpse into the real-world implementation of HPC with container technology. So first, thank you. I'll hand it over to Matthew Scambati, who will talk about software quality assurance for high-performance computing containers. Matthew, take it away.
Thanks, John. Hi, everybody. Thanks for taking the time to be here today to let me talk to you about this. It was a pretty exciting topic to me. We have our traditional software stack where, every site's managing, I would assume anyways, some type of module system and a bunch of applications. And, when you have numerous HPC systems, moving those applications from cluster to cluster gets tiresome, right? It can be very tedious and take a lot of time. And so we started playing around with containers about 2 years ago. And we want to try and come up with a good way to make sure that we have some longevity and reproducibility, portability, and everything else that containers provide here when it comes to our software stack. So we wrote this paper about software quality assurance for high-performance computing containers. And let me talk to you about it. So why are we doing containers, right? We want to do verification and validation. Most of our users, from a user perspective anyways, they want to know whether or not their code's still going to run in different environments. If I move from a Rocky 8 system or a RHEL 7 system or even an Ubuntu system, is my stuff going to work the same? Typically it won't. So containers here will let us take advantage of their ability to be portable, right? And reproducible. So our next topic, reproducible, right? So how long can I run this for? We have a lot of codes here that people will need to go back 10, 15 years and rerun something. We need to validate data sets, outcomes, things like that. And so containers give us that ability. Now, like I mentioned, portability across architectures, right? What can we do here to help minimize the needing to rebuild applications over and over and changing that software stack? Containers give us that. Simplification. So this one's a big one for me. I help a lot of users compile code. And you know that when you compile code on different systems, it's different libraries, nothing's ever exactly the same. I mean, I guess unless you have identical hardware and identical everything else, sure, but typically you don't, right? This gives them that one environment that can build in, create an executable, and then use it everywhere else. And then security more from a standpoint from the user's perspective of, If myself as a system administrator, right now we're in a big outage. We're upgrading our flagship system Sawtooth from CentOS 7 or RHEL 7 to Rocky Linux 8 and Red Hat 8. Is that going to break their code? Of course it's going to. Well, what happens when I do typical security updates? That has an impact as well. Whoops. So let's talk about how you typically create a container. I don't like to make assumptions, so I'm just going to go over this quickly. But if you've never built a container before, anytime you Google this, the first thing they'll probably have you do is do some kind of Docker pull. If you use Singularity Apptainer, you do that as well. But it's some kind of pull process where you reach out to one of these environments, and then you create some library of containers that someone else has already built. But let's talk about doing it with a definition file, right? You do the same thing, you write a little script, and when you pull down this container, you do a build process, and then you get this nice black box. But it works, right? So what happens when we want this to be reproducible? It's not, if depending on how you write your piece and everything that you do here in your definition file, stuff in the cloud changes, right? Singularity can change, Docker can change, or our package repository can change. So I'm not guaranteed if I run that script again to get the exact same container over and over. I'm going to get some different one, even on the same day if I build it again, and all depending when packages get pushed out. So we need to have it where we can guarantee everything that's the same. So this is where we came up with this idea of like, let's try and do some kind of layering system here, right? And if you've ever done a definition file, technically you've done a layer already because you're pulling from some base cloud instance, unless you're doing it from your own package repository. But you really are, right? You're pulling from something, building one already, and then putting your special piece on top of it. So we take that initial image, it reaches out to the cloud, and then from there, now it's static, and now we build off of that over and over to create these different layers of our container process. So let's talk about, since we're in HPC here, it's the two primary components that a lot of us care about, MPI and InfiniBand, or some type of high-speed, low-latency fabric. It doesn't have to be InfiniBand. It can be OmniPath or high-speed Ethernet, whatever you want. There's two primary approaches when it comes from the Apptainer or Singularity perspective. We can have it where we either do the hybrid approach, where you have a system-level MPI and a system InfiniBand. For this slide, I'm going to talk about InfiniBand. Please replace it with whatever backend you want to use there. But then you have the container MPI and a container InfiniBand. Or there's the bind method. And the bind method, what you have to do there is take in stuff that's installed on the system and put it into the container. Now you're extremely restricting your container to exactly what's on that host. And a requirement of that is that the host OS and the container OS have to be compatible. With the hybrid approach, we don't have those restrictions. The only compatibility, or the only thing we have to worry about there is that the MPI is ABI compatible, and that the InfiniBand or OmniPath or whatever is series compatible. And so as long as those drivers and MPI are capable of communicating with each other, the container OS and host OS don't have to be compatible in that regard. And it makes it a lot easier from a system administrator perspective, where now, or software stack manager or whatever your role is in that regard, you really now just have to manage drivers and MPI when it comes to your applications. So here's our strategy. Taking from this and understanding those little pieces I talked about there, so we have three key components. HPC applications are built via this layering system. We kind of came up with this triangle approach here. Every key component is grouped into a single layer, and each of these can be updated and be reproducible because we use local mirrors. So we can update each layer individually. And then one of the strategies that we do here is that we create a static local mirror of all the packages. And then we point all of these different layers at that system so we can guarantee the same build over and over from that. And the goal here is that from the bottom up is the bottom stuff changes the least and the top stuff changes the most. So typically, you'll hopefully only have to build here from the top. Now, you don't have to build all the layers all at the same time. Like if you're building the application and really all you need is this base plus layer, you can build your application straight from the base plus layer. You don't have to use all these other layers, but you can pick and choose in that regard. So we do make some key assumptions here, is that the host systems will use LTS supported versions of drivers and software stacks, and that the system administrators will be willing to install an ABI compatible version of MPI if it doesn't exist. So let's look at a basic file. All we're doing here is just capturing some system specific Sorry, I should have asked, can you guys see my cursor? I don't know if I should use the laser pointer, I'm sorry.
I can see your cursor.
Okay, thanks. So all we're doing is capturing some build information here. So this will help. Hopefully, the thought here is that, you know, in 8 years from now, I might need to know everything about the system that the container is built on. I can't foresee the future. I don't know where containers are going to go or where things are going to change. So update this and put what you think is the most relevant for your build process in here. So this is a very basic one. This is the only thing in that pyramid that reaches out to the internet. After that, everything else, so this is the base plus one where we add the compilers and other helpful, useful tools, points to our local static mirrors here. So instead of reaching out to the internet, we point to our local mirrors that we timestamp and capture the same information in every layer for that one. So the next layer, this is where we install the different interconnect pieces. And so here we're installing InfiniBand and OmniPath. I have some newer versions where we've installed some high-speed Ethernet driver stacks, and we're going to get a test system here of hopefully in the next 2 months of well, I can't think of the other one, Slingshot. And so it'll be interesting to see if we can put all of those in this one layer or not. So that's one of the big things here, is that you don't have bifurcation in your build pyramid. You want to try and keep it as simple as possible. So hopefully all of those will fit in one stack and not interfere with each other in one layer is what I meant to say. And then on the next one, this is where we can put all the MPI for this piece. And this is where we rely on the ABI compatibility layer. And there's actually some very interesting work when it comes to this. I do apologize that my phone was on. This ABI compatibility layer is in March or April of next year. The committee that runs that is looking to push out new versions of the ABI instances for MPI, which means that we can then change all of these layers here to be a much more simplified version, where we can include a standard ABI header essentially for all of these, which will be really nice. And then it won't matter if you're using OpenMPI versus MPI-CH, MPitch, whatever you want. So right now there's kind of two base flavors of MPI, and I should have mentioned this a little earlier, which is why we have the two in here. There's the MPitch ABI compatible versions, and then there's the OpenMPI compatible versions. And so for MPitch, you have Intel, MVAPitch, and others. And then for OpenMPI, you have OpenMPI itself, NVIDIA's, and there's one other one I can't think off the top of my head. So you have a few that you can pick and choose from. So we decided to build a bunch of test applications for this, and then we tested them on our varying systems here. So out of the 4 systems that we have, Sawtooth, Limhi, and Hoodoo were tested both for compatibility, portability, and performance. And then Galena was just tested for portability. And so, as you can see, we have different architecture here, different operating systems, and different interconnect fabrics running different driver series. And we were able to get some unique results from this. I do apologize, I need to turn the camera off. I can't see my own slides. 1 second. So from here, running Lulish, for example, we did 1,000 iterations here. And then, sorry, I can't see my notes, so I don't remember exactly all the metrics here. It's all on the paper. But as you can see, we were able to get some very good performance metrics between the native version, which should be optimized very well, and the container version. And in some cases, the container version is faster than the native version. And so for this one, you can see it between OpenMPI and MVAPitch. And like I was saying, since there isn't one kind of MPI, EBI layer here, we do have to build the application for both types of MPI, for lack of a better phrase. So here it is on Limhi and Hoodoo. We had, again, very similar results between the container and the native built application, where one wasn't extremely more performant than the other. The most extreme swings that we saw on this is about 14%. So, and I'll talk about that a little more later. We also did the OSU benchmarks here for all the all on 10 nodes on Sawtooth using OpenMPI and MVAPitch. And we see here that the OpenMPI version, for example, they are extremely close, did a very good job of the container performing very well there. And then when we had some discrepancies here, we did We're not exactly sure why on some of these pieces, and I still haven't had time to investigate it. But on some of them, when we look at these, and it'll come up after the OSU benchmarks here. So the container and the native perform really well on Hoodoo as well as Lemhi. But when we go to MCMP, for example, you'll notice that actually the native is a lot faster in some cases than the container, or the container is extremely faster. And what we found here is that we just actually didn't compile the code well and optimize it well on the host system, so the native system. So this showed that we needed some improvements on our end when it came to our native compiles. And so in the end, I just went over a strategy that shows we can have portability across different supercomputing architectures. We get that reproducibility due to the layering scheme and the local mirrors that we have. I didn't talk too much about traceability, but this is a big one for a lot of your software Q&A processes, right? You need to know what you're doing at every step. And so having a definition file at each layer showing only the differences between all those layers makes it a lot easier to track what was done at each one of those layers. I mentioned a little bit earlier that it simplifies the fact that now the HPC staff really only has to worry about MPI, ABI compatibility, and interconnect compatibility. And then it really insulates the users from a security standpoint as we do updates and changes on the system. That's all I got. If anyone has any questions.
I've got a quick question. At least I think it's quick. Between the native runs and the containerized runs, how are you handling processor pinning?
So we didn't. I didn't run those. So if I remember right, we did not do processor pinning, which we should have, and that's more analysis that could be done. It's a good question.
Any other questions for now? You'll still have probably another opportunity at the end of the hour for more questions, but
the one thing I guess I'll say is I did mention it already, but I really want to emphasize the fact that new API release for MPI will be a huge boon for this. I'm pretty excited to see that. That'll simplify some of these layering processes. And we are, I kind of wish this call, I should have taken the later one. It just didn't work for me because we're right in the middle of upgrading Sawtooth. So that'll be a big test for us to see if this strategy will actually work as well as we believe it does. So I'll have more answers in about a month once we redo that whole stack and see if it works out.
Hi, Matt. I have a question.
Sure.
How are your users, like, how do your users know about this new way of running their research code? Like, did you market this, or like, are you pushing this? Is it mandatory to use containers in your environment, or is it up to their discretion?
Great question. It's not mandatory yet. I would like to get it there. So for certain applications, we've just created some modules and scripts where it's seamless for the user, so they don't have to change their submission scripts. And so we let them run with the native way that they're used to. And when they run into issues, the first thing I do in any support ticket is say, oh, hey, try the container version. And so far with about, I don't know, 60 or so tickets, it's resolved them all with a simple, just go use the container. And I've gotten a lot of great feedback of they're very happy now because they can run on both Sawtooth and Lemhi seamlessly with no problems. We're hoping at the end of this big outage in about another 2.5, 3 weeks to make an announcement pushing that the new stack for Sawtooth, most of the applications will be this container-based, be using this strategy. And make sure to tell users that, you know, it's no impact on their side. They don't have to do anything extra. They can just run all their stuff exactly as before.
any more questions for Matthew?
I got a question for the group. No one's got any. Anyone see any big flaws or holes or anything I'm missing here? Or, you know, I'm not an expert here. I just thought this would work out, and so far it has. So anyone got, I mean, there's better people at this than me, so any feedback on this would be greatly appreciated. And that's not to put you on the spot now. You could always email me or chat me or something. Sorry. Not everyone likes to be put on the spot. That I didn't mean it that way. But if there's any feedback or anything, I would appreciate anything you guys got.
Yeah, you signed up in the call document, so other people can see your email.
I can't get to the doc, so
Okay.
I'll put it in
Yeah.
chat if one of you guys can do that for me.
Yeah, we'll do that.
Thanks.
All right.
Matt, I do have another question.
Yeah, sure.
When you build your container, your apptainer,
Mhm.
do you store it right like on a file system, or do you put it into like a repository that's
Oh, I didn't talk about that. Great question. Sorry. Yeah, we use Harbor, which is an OCI registry. Open source. It's awesome. I really like it. And so, and yeah, I guess that's mainly what we use. We make sure to make the version match the def file with whatever's pushed up there. We suggest users to use the version versus latest, but it's up to them if they want to build their own piece. And when users want to build their own container, we just point them to the Harbor instance and say, you know, search on there and find whatever layer of the stack you want to use and pull and build your own thing. It's a ORAS protocol, if I remember right. And yeah, if you want any help with Harbor, just reach out. It's a really nice tool. It's really easy to install and set up and works great.
great? Thanks, Matt.
Mm-hmm.
All right. Thank you, Matthew, for that overview on the layering strategy for building containers. Now we will hear from Xin Liang about using containers with real-world implementations of HPC. Xin, you want to go ahead and present and take it away?
Can you see my slide?
Yes.
Okay, great. Thank you. My name is Xin Liang. I work for WashU, and I'm in the research infrastructure services. I'm the solution architect at the department. So today, well, thank you for inviting us to present over here. And today I'm going to present the HPC with Docker. So why we use Docker? I present that at the PERT conference and talk about all that. I want to show this briefly. Why we use Docker initially is because Docker came out first, and then we keep an eye on the container, and then we do some POC and try out on that, and then we have our first Docker registry around 2014. And then we have our whole cluster converted to Docker using Docker with LSF around 2015, before the Singularity came out. And then we have a THPC. That's the short paper I presented at the PERT 23. And when we choose Docker, actually, what we did is that we have some objective in mind, what we're going to do. One of the things of Docker is that it's a flexibility. You can use different OS, Ubuntu, CentOS, Red Hat, and many Linux OS you can use to build your software, to contain your software you want to run. So that's the flexibility of that. And the other one is we want to make it simple too. So we look at our infrastructure, our infrastructure set up, and how we're going to make it simple that we can integrate with the container system. And certainly we want to start where we are. We don't want to reinvent the wheel, right? So for example, we have our infrastructure, we have our scheduler, we have our storage, all that. We don't want to change it. We just want to use the container system. So that's one of it. And the other thing is important is the security. We want to make sure the security, right? We don't want people to hack into the container or to do something malicious to our system. So the other important part is security. But when we started, the objective, you can see I have it in the order like flexibility. Flexibility is very important. And certainly security, but we still want to do it. For the user, they don't care. They just want to run their stuff. For system, we want to make sure our infrastructure is secure. That's why we have the security over there. And one of the things is that we're using LSF actually, scheduler. And what we work with the vendor and ask them, how can we run Docker? And they give us some idea of how to do it. So basically for the flow diagram over here is job submission, and then scheduler processing is like ESUB, and resource, after you get the resource, it will go over to the execution node and run the Docker wrapper, and it will retrieve the image and gather the file system directory and run the Docker run. So that's the flow of it, of the whole system to get to Docker run. So what we have from the LSS scheduler, we talked to the vendor said you can use the -A and plus the Docker ESUB, and you should be able to do it. I have an example over here. It's very simple. Basically, ESUB -A Docker Ubuntu 2004. And then you can see if you use the LSS before, without this one, it's like basic submission from the LSS, like ESUB -ls interactive shell bin bash, right? What we did is we only added a small option over here, Docker. So it's very simple. We want to make it simple. We don't want the user to need to learn a lot of stuff. We just want to have introduced a new one option. That's all. And then they can use the system without any big change from their part. So is that job done? I don't think so. So what I talk about is only the flexibility, simple, start where we are, but I haven't talked about security. So let's talk about the security. So you see, I only have talked about this. I never talked about the security. Let's get more info about how we're going to secure our Docker environment. The first thing what we're going to secure is a Docker daemon. What we did is that we're using the -H, using the Unix socket to make sure no other connection from the outside of the host can connect to the Docker. So we're using the Unix, the IPC socket over here. And then the other thing what we did is that we want to make sure when you're inside the Docker container, if you somehow you get hold to a root inside the Docker container, you cannot do a big damage. We want to remap the root ID or any ID over there to the higher ID. It's not a 0 ID. So what we did is that we're securing the Docker daemon using this two, -H for the socket, and the user namesake remap for the user working inside the Docker container. After the Docker container daemon is secure, we need to secure the Docker container to the instances running on the host. We want to make sure everything is secure. Everything what we know about, we will need to secure it according to the best practice. First thing, we need to run the Docker container as the user. And when the user inside the Docker container, they're not as a root user, it's as the user itself. So what we did is that we're using -U, UID, and GID for the user. And the other thing is that we will need to make sure they're not using the whole machine resources, right? Basically, we need to limit when you submit a job using 2 CPU slot in LSF slot, how many slots you have. If they specify 2 slots, we need to limit only 2 CPU or 2 thread, depending on how you configure the slot. So we use the CPU share to limit that. And then the other thing what we did is that we drop all the capability for the Docker first. We only add what the user need. And the other thing what we did is that we do a security option to put the SE Linux label into the Docker container. And also we also limit the memory size, make sure they're not used more than what they're requested. And we also no new privileges for the security option, except the one we put in for the SE Linux. All other options I mentioned here, the most important thing, we override the etc password and the group inside the Docker container. So what you put in, you create a Docker container with a sudo privilege or some other thing in there, it will not work because we override the etc password and group inside the Docker container when the Docker run started. So this will prevent malicious people to get a hold of certain privileges account or group. And the other part of the system, right? You have compute, you have storage, you have memory, and we need to secure the storage. We have primary storage, is a storage cluster, and then we have a home cluster for user home directory, and then we also have Scratch storage for people to put the data in there to run their HPC workload, because Scratch storage is a NVMe, high performance storage. How we do all those, we're using the Docker mount option to mount all those into the Docker container. Actually, we're not mounting the whole file system, it's whatever the user have access to it, or whatever they're requesting it, we'll mount it into the Docker container for them. And we also have the temp space provided to each job for that. And on top of all those storage, we have ACL to control access control. And we also have SE Linux on top of it to make sure everything is kosher. And one of the things what we do is all our server have SE Linux, we have Splunk, log into the Splunk, and we have CrowdStrike to make sure to scan the process to make sure all the process is good. And then we're also using the Nexus vulnerability scanner to scan it. And the other thing what we have, certainly I talk about that, we have ACL. And one of the things is that no user except admin can access it to the exec node. No user can access it into the exec node. So basically they cannot go into the node and see stuff. They can just do a bsub into the system. And the paper I wrote with Quick Paul, the short paper for the PERC conference is about THPC. Just now, I talk about is the infrastructure, how we use Docker and all that. And then we have, on top of that, we have a system, THPC, using the Docker layer. What we did is that we have LSF submit a job, and they can use all the software we put into the software repository. This is the basic diagram of, we have LSF job, we have the container, we have all the node here, everything is go through the InfiniBand, and all the software we have is put into the NVMe storage. And all the job can use the software. We have hundreds of software over there. They can just say module load, MATLAB, module load, Intel compiler, one API, Intel load, some other software. As you know, building a Docker container with all those software, gigabyte of software, it will take 10 of minutes, maybe hours just to load the container. That's why we came up with the THPC to separate out the OS, whatever important what you have is in the Docker container. If you want to call the software, you can call that to the a cluster storage, the fast NVMe high performance storage system to call your software. And I'm going to give a demo quickly over here. So this is the open on demand. Basically, it's using the Docker container, submit a job, bsub a job, and then run a job using a Docker container in our cluster. So I'm going to start the video here. So we have that, click on that, and you will get a GUI, NC session. You can do a module load away, and all software is over there. And what you see, all the software actually is a persistent storage. It's not in the Docker container. And I can do a visual code. For example, we have one of the module is visual code. I can load the visual code and bring up the GUI over here. And the visual code actually is not locally in the Docker container or Docker image. It's on a high performance, storage. And the other thing I want to show is that, for example, there's a lot of workflow out there like Confluence, Nextflow. I just want to give a demo. Recently, I worked with a few researchers on the Nextflow. I want to demo how we can run that in our cluster using the Nextflow over here. So one of the Nextflow module I'm using over here is an MC Micro. I believe when I worked with the researcher, he told me that nobody successfully run that in the LSF environment, not to mention inside a Docker container, HPC cluster with Docker container. So I'm going to make it faster just to show you. It will run the whole thing. I think the whole thing take about 6 minutes to finish. I'm going to speed it up. So the only thing I changed, you can see here, the command I run is Nextflow run, and then the MC Micro, and then that's the input data. The only thing that is special over here is the configuration. What I did is that I'm using the -C test config over there. So one of the things what I did is that I changed the cluster option to use the LSF option to run that in our cluster, and also -A to call the Docker container to run the job. And the other thing, like Matt mentioned about MPI and how to run MPI using Docker. So I'm going to give a demo here, how I run the MPI. The first one, what I gave you before the Nextflow, you're using the THPC. Now I'm using the bsub, just basic bsub with the -A with the Docker container that I built for the basic Open MPI run. So the demo over here, what I have is to compile a Hello World MPI that I downloaded from the web, just a Hello World MPI Hello World. After I compile, I can run that in our cluster across node. And if you use the LSF before, the -N4 is 4 slot. And then for the span P tile equal to 2, meaning each host you will have 2 slots occupy a host. So what I did here is occupy 2 hosts. You can see that I have an exact node of 135 and 131 across node. And this is just an example, right? I'm going to give you a more advanced WRF MPI. I just created this video this morning. Yesterday, I was helping a user that want to run WRF using the Intel compiler. He was able to run with the Open MPI, but he want to be using Intel to customize that for the Intel processor. So I helped him to compile that and show him how to run that using a basic Intel 1 API. And all the data actually is stored into a persistent storage in a Scratch 1 in my space. So I'm going to start the video. Basically, I will get a job. And it's landed on exact 85. And then I will set up the environment a little bit because I need to set up the library, all those Intel library and all the WRF library have been compiled. The user have compiled. And go into the WRF directory that user created, but I copied that into my persistent storage. I'm just mount it into OPT WRF and run it. And what you see down here it have two Docker pull because it's running in two nodes. So it pull twice and run it. And that's the result of the WRF run. And this is the paper I presented at Perth. And me and Craig Paul are the author for the paper. And any question?
Please feel free to speak up and ask your question or post it to the chat.
So I have a question, and I feel a little unfortunate asking it because it's more about your use of CrowdStrike rather than the container tech. I'm just curious, where does CrowdStrike run on your system?
Where the CrowdStrike run in our system, the CrowdStrike run on the host, basically, and then we have the central web from the CrowdStrike, so it will do a scanning on our host. We have the agent run. I think it's called, what's that? I don't remember now. We have the agent run there. Yeah, and we also have the agent run on the host too.
So follow, sorry, Matt, go ahead. To follow up on that, do you do like any kind of C grouping for that process to constrain its resource usage on the node?
What do you mean by secret?
C grouping. So, you know, constraining the
C group. I don't see.
Sorry.
Yeah. So yes, that's what we do. We do have a constraint on that using that. The Docker container, one of the things I show you is that we do limit the resource on the Docker container itself. And then we also do a U limit on the Docker container, what they can spawn, how many processors they can spawn to.
So if I can just ask for a minor clarification on the CrowdStrike piece. So when you say the host, is it running only on the login nodes, or do you have it running across compute as well?
Across all the compute nodes, all the exact node.
Cool, thanks.
This is our standard for all our machine in our university. The InfoSec want us to run all those in our cluster.
What do you do for logging? You might have mentioned, I just could have missed it.
What do you mean, log in?
Since you're running CrowdStrike on all your computers as your security posture, like what do you do for grabbing all the logs of what's happening on those systems as well?
Maybe Craig can answer that better than me.
Yeah, so it all goes to, all of the logs go to Splunk, and that's where our information security team analyzes our logs. As you know, as like I should mention, we run CrowdStrike and all the servers. We started out just on the edge devices like the login nodes and other storage servers, but then there was a push this spring to get it on every device, and so we said, all right, well, we'll give it a try, and it hasn't caused any impact. And then they also do tenable scanning, which has caused some impact on our gateways. We've seen our gateways drop off when they do that, our InfiniBand gateways. And so they're actually going to build a dedicated server on our InfiniBand network to do scanning.
If you don't mind, I got another one. Do you guys allow internet access from your compute nodes?
Well, I mean, direct. I mean, so we recently made our open on demand, public accessible. Everything was only allowed from a WashU network, so either VPN or on campus network. We recently made open on demand because even that just got confusing to some of our users. And so we said, all right. And so we put it wasn't. So the other thing is that we put it in the F5 in front of it, and another security strategy. So the only thing directly accessible from the internet is our open on demand and Globus endpoints.
Thanks for your clarification. Appreciate that.
You're welcome. Any other question?
Shane, I've used Docker rootless. Is that what you're using? Or is it just regular
No.
Docker?
Just regular Docker. We're not using Docker rootless.
Any other questions for Shin or Matthew? Or maybe more security questions, since that seems to be a popular topic.
Yeah, I mean, I think so we support, so we're a large medical academic center. So when we built the latest version of our storage and cluster, we wanted to support HIPAA and PHI data. So that's why we're doing all these things. But it is used for general research, and we do have large scale simulations in MPI. As far as we're concerned, 2,000, to 3,000 core simulations. So is large for us and our largest user. But all within the same security environment. I mean, the cool thing is that researcher, when it came to us, they had tried to run this old Fortran code and move it to the cloud and run it there, and they couldn't do it. And he was recruited to the university, and so we helped him containerize it. And so now, I mean, that's the beauty of it, is he can compile it with different compilers easily and run it anywhere. And that's what we see, with a lot of our researchers. Like, if they can get started with us and build the container, like they'll be like, hey, I got a deadline, I need extra compute. And because they have it in a container now, they can go to a cloud and run it there and pay for that, if they need extra compute resources.
And why didn't you just go with Singularity? What was the big driver with just going with Docker?
That's a great question. Yes. As I mentioned during the first slide, the reason we are not going into Singularity because we have the whole thing set up initially with Docker, and then we did keep an eye on Singularity when it came out, and we just look at that and then say, yeah, we can support that. We can put another -A Singularity and support Singularity easily. But since it's fulfill all the researcher at that time, what we have, we just can't go with one because there are not really many researcher requesting for the Singularity.
Yeah, we were such early adopters to Docker, and a large number of our users are in the bioinformatics community. They were the ones that were driving this and maintaining the software. At the time, 8 years ago was very time consuming, and we could move as fast as they wanted. And so it's kind of why we adopted Docker, and then, really when Singularity came out, we thought it was, really just, it was somewhat an optimization of some of the processes, that are slow in Docker, like the Docker pool and, getting the image and running it. And so, and there's other ways to, I don't know, at least some of our sysadmins at the time thought it was other ways to just optimize the process too. So we do some things, the containers, when they're pulled down, as far as, that becomes a problem when you're running a cluster, is like container caching and stuff like that. I mean, so it does help speed up the process, or it does create, temp space problems. So that's sort of things to think about, when you're running Docker at large scale.
Right, and we have time for one more quick question from the chat. This is from Jim Lawson. Craig, exposing on-demand web interface to the internet. You mentioned putting F5 in front of it. Is that the LTM product, load balancer, or are you using another F5 product such as WAF?
Yeah, it's the load balancer and security scanning.
Thank you, Shin, Craig, Matthew, for presenting today on usage of containers and HPC. A couple quick final announcements. Just a reminder, there will be no track call next month in spirit of SC. So if you are going to be attending SC, please say hi to either myself or Matthew, who I know will be there, and I'm sure a number of others will be there as well. And then we will not be having a formal call during the December timeframe, but there could be a holiday party / recap of the year that will be planned. So more details on that to come. But thank you all for coming, and hope you all have a great rest of your day.
Great, thank you. Bye.
Thanks, everybody.